Good morning. I started recording the video. So, welcome everybody. I'm sorry that we see each other only virtually for 2 times in a row, and I'm confirming that on Monday I'll teach in presence as usual. And then just remember the calendar. Next week we have a lecture on Monday only because on Wednesday on Thursday the Easter break starts, and then we will meet again after the Easter break and the Thursday after the Easter break. You see here the calendar of the lectures, which is unchanged. So today is March 21, and March 25 is Monday, and then April 4 we have it's a Thursday after the Easter break, and we have 2 hours online again. So we started talking of risk-based adaptation design. I'm clicking on the lecture. And last time we started the nasty topic of probability estimation, which we did by also using some numerical simulation into R. And here I'm scrolling down the lecture in order to remind you where we are. And in particular, we introduced the risk equation, and once again, this is a very important topic. It's a very recurrent question at the exam, so please be aware of that. And the risk equation is, as you know, is obtained, the estimate for the risk is obtained by multiplying probability, vulnerability, and exposure. And then we discussed how to estimate exposure, how to estimate vulnerability. And remember that vulnerability is in the range 0, 1, while exposure is expressed in units that correspond to the measure, the unit of the measure that we use to quantify the risk. Okay, so maybe economic unit or whatever, loss of lives, whatever. And then we have probability estimation, probability of the considered hazards of the considered event to occur. And then we started the discussion on probability. We defined probability through Kolmogorov axioms. And again, remember them because they are, the definition of probability is fundamental for what we have to do. And in particular, we discussed probability estimation. So we defined probability and we discussed probability estimation. I'm scrolling down the lecture. Probability estimation, we said that can be done in 2 ways. And one way is the frequentist estimation. So basically we count the frequency, we estimate the frequency of the event during time. And this is what is usually done in when dealing with climate. We try to refer to observed data, and then we estimate the frequency of a disaster to occur. And then we have the Bayesian estimation, which is an estimation that is based on not on an experiment, not on an estimate of frequency. It's an estimation that is based on our knowledge. So we use our knowledge to get an estimate of probability. Now, we also defined the cumulative probability. And we did that because, and here we get into the topic that I want to discuss with you today. We said one important thing. Probability estimation, it's, can you please turn off your micros? Thank you very much. Probability estimation is, oh, sorry, there is a micro that is open. So who is the micro open? Let me see. Okay, it's turned off now. Okay, so as I said, probability estimation is relatively easy when we deal with discrete variables. So we discussed tossing a coin, we discussed rolling a dice. The result from the experiment is a discrete variable. And therefore, in this case, we said it's relatively easy because we count the number of times that each possible outcome from the discrete variable occurred. So in case of rolling a dice, if we are interested in the probability of getting a 1, Then we make a series of experiments, and then we count the number of times the outcome of one occurred. And then we estimate the frequency, because once that we counted the number of times an event occurred, it's easy to estimate the frequency. Good. For the case of rolling a dice, we can define also the probability of not exceedance. And look at the equation that you see on the screen now, in the center of the screen. So if I want the probability that an outcome is lower or equal than 4, we just need to sum the probability of all the outcomes that satisfy the requirement. So probability of, read the equation, I equal or less than 4 is given by the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. And we said that this is the way to compute the probability of not exceedance, which is the complement to 1 of the probability of exceedance. So I try to be clear on that. The probability of the result equal or less than 4, look at the equation, is 2/3. What is the probability of exceeding 4? Is 1 minus 2/3. So the probability of not exceedance for a given number is the complement to 1 of the probability of not exceedance. Okay, and this is a result of the Kolmogorov axioms. Okay, good. But we are still discussing a discrete variable. And then we started just 5 minutes last time to discuss how to deal with continuous variables. And let me just get back RStudio. Okay, here it is, and just let me clean everything. Clean everything. Very good. And now I clear the console. So last time what we did was to start dealing with the continuous variables. Okay, and I made an example. I said, okay, let's suppose that we generate a continuous variable. Okay, and let me see, what I did was to generate a vector of real numbers into R, 1 million of real numbers. So I did this. Data 1 is equal to random generation. You can use this function, and then you put 1 million. Okay, this is random generation, and if you remember, I plotted it. Okay, if I plot 1 million numbers, the plot becomes messy. Let me plot only a fraction of it. Okay, data 1 from 1 to 100. Okay, and let me use a line to connect the plot. If you have any question, write on the chat. Okay, I'm looking the chat here. 1 second. Okay, perfect. Let me see if there are people in the waiting room. No? Good. You see the plot. This is a random number that I generated with R. It's a random number that is between 0 and 1. And then I said, if I try to estimate the probability of this continuous variable, like I did for I'm sorry, I had to switch off the phone. This is why I interrupted. If I have to estimate the probability of a given value of a continuous variable, and like I did for the discrete variable, so for instance, let me estimate the probability of 0.5. If I try to estimate the frequency of 0.5 in this vector of real numbers, so let me just get length data 1 with the condition that data 1 is equal to 0.5, okay? And then I can divide the length of this vector for 1 million. You see, it's 0. So I get no numbers with value of 0.5. This is clear because it's a real variable. So it's impossible that I get from a random generation, from a random experiment, I get the precise real variable which has an infinite number of digits. Okay. But what I can do, I said, is to estimate the probability of not exceedance. I can do that. I can do that. And given that the random generation was done in the range 0, 1, what probability would you expect of not exceedance for 0.5? It's random numbers equally distributed in the interval 0, 1. What I am expecting is that I get a frequency of about 0.5 of numbers that are less or equal than 0.5. Let me try it, okay? Instead of looking for the data that are equal to 0.5, let's look for the data that are less or equal than 0.5. Okay, let's see. And then the number of this data. There is a micro open once again, if you can please switch it off. And then I divide for 1 million, which is the total number. So you see the probability is precisely 0.5. So the probability of not exceedance is 0.5. Okay, let me see. So Masume Kavei, please switch off your micro. Thank you very much. Very good. Okay, so basically with a continuous variable, and this is the conclusion, the synthesis of my narrative so far. With a continuous variable, you cannot estimate the probability of a precise number, but you can estimate the probability of not exceedance. Okay, this is fine, and for us it may be enough because we are interested very often in the probability of not exceedance of, for instance, a water stage, a river level, or probability of not exceedance of a given intensity of an earthquake. Remember, probability of not exceedance is equivalent to the knowledge of the probability of exceedance, okay? Because they are one the complement to one of the other, okay? Perfect. So, for instance, in this case, let me now refer back to R. Let me estimate the probability of not exceedance of 0.3, okay? 0.3. You see, it's precisely 0.3, which is what I was expecting. The probability of exceedance is 1 minus. This is the probability of not exceedance of 0.3, which is 0.7. Okay, must be clear. Okay, any question on that? So we solved our problem even with the real variables, provided that I'm not focused, I'm not interested in the probability of a given outcome. I'm not interested in the probability of 0.3, but I am only interested in the probability of not exceedance of 0.3. Good. But what if I am interested for a real variable in the probability of 0.3? What is a way to solve the problem? Because in some of the cases, I may need also the probability of a given number. So I really want to know the probability of 0.3. I cannot estimate it as I did so far into R by counting the outcomes, by estimating the frequency. I can't do that, okay? So how can I solve the problem? This is the last complication of our discussion on probability. Once we solve this problem, then we are done, okay? Very good. Now, let me go back to the website for this discussion, okay? Okay, there is a box of R software, and which you don't need because you already know what R is. And there is an exercise, computation of probability. We already did this with the R software. It is what I just did, okay? Now, let's look at the continuous random variables. And what may be a strategy, okay, to estimate the probability of a given number. Let me open a graphical window in order to better explain what I mean, okay? So, 1 second, because I need to open it. Okay, here it is, and. Very good. 1 second, I move it on the screen so you can see it. Okay, this is a graphic blackboard. Good. Now, let me draw over an axis the variable. So let me draw over an axis here my variable x. Let's call it x, okay? When we identify random variables, we usually use capital letters. So when I want to identify a random variable, like for instance, earthquake intensity, I can call it X. The important thing is that I identify it with capital letter. It's not really important, it's a convention, okay? And a specific outcome is identified with lowercase letters. I try to explain better. This is the axis of my random variable. And in particular, in the generation that I did so far, the random variable was varying in the interval 0, 1. Okay, so this is 0. Okay, and this is 1. Okay, and let's identify the limit. Okay, this is 0. Sorry, this is 0, and this sorry, and this is 1. Okay. Okay, perfect. So this random variable, I may have several outcomes. Into R, I generated 1 million of outcomes. Okay. So when I want to generically indicate the random variable, I say random variable capital X. If I want to identify a specific value, which may be, for instance, 0.3, let me place it somewhere here, 0.3, then I say lowercase x equal 0.3. Okay, so the specific variable usually, in conventionally, we indicate it with a lowercase letter corresponding to the uppercase of the random variable. 0.3 is more or less here, okay? So I proved that we can estimate the probability of not exceedance of lowercase x equal 0.3. But what if I want to estimate the probability of x equal to 0.3? Okay, because in some of the cases, as I said, I need it. So if you think to an earthquake, I may be interested in the probability of getting an earthquake with magnitude Richter 10, in the Richter scale 10. Okay, so I may be interested in the probability of a precise value. Okay, so how can I do that? Okay, there is one possibility, which is, given that I cannot count the outcomes that are precisely equal to 0.3, because I have no outcomes that are precisely equal to 0.3. One possibility is to identify an interval around 0.3. Let me identify it. For instance, here, the interval that starts from here. Let me just change the color, because in this way I have more clarity. The interval that starts from here to here. Okay, and let me identify this interval with a measure. Okay, so the measure may be, for instance, let me put a quote line here. Okay, here, here, and here. Okay, so the measure of the interval may be something like delta x. Okay, here and here. Just 1 second. Okay, here and here. Okay, good. And then I can count the number of times my random variable falls here. Okay, so I can estimate, I can count here the number of times, and let me write it here. I can count the number of times x is included in the interval. Just 1 second, I make it visible. And therefore I can count the frequency x is included in the interval. This is an idea. I mean, given that I cannot get the precise outcome lowercase x equal to 0.3, I fix an interval and then I count the number of times the random variable falls into the interval. Okay, and of course, where you have a higher probability, you will get more counts. Let's go back to the website and see how we can write it in a formal way. Okay, so you see here an empirical solution for computing the probability of getting an outcome x from the random variable capital X, namely lowercase equal to uppercase. Maybe here there is a b that is missing. Okay, maybe to split the domain of x into segments with finite length and then compute the frequency of the outcome x falling into the interval. Just 1 second. I want to make the correction online of these mistakes, and because there is a b that is missing and there is a plural that is missing. So just 1 second, and I am making the correction online. So give me 1 second. Okay, this is perfect. And then let me, okay, let me just do this. Give me 1 second once again. And I need to, I'm working in another window, so I'm not showing on the screen, because otherwise I make confusion, and then I can make also other corrections directly. Okay, risk-based adaptation design, perfect. Edit. Okay, let me make the correction, maybe to split. Okay. And if you see other spelling error, just let me know. Maybe to split the domain into segments. Okay. Good. Okay, let me refresh it. Okay, maybe to split the domain of x into segments and then compute the frequency. Perfect. So in a formal way, what we have to do is then to compute this quantity frequency, which I indicated with the symbol FR. Okay, so basically I go back to the graphic window, FR. What I indicated here, I am computing the frequency FR x minus dx x plus, sorry, this is, okay, here, x plus dx. So I can compute the frequency, okay, for each interval, for each x value. This is not difficult. However, if I make this computation, you understand that the result depends on the width of the interval. So if the interval is larger, if I increase the x, I get more outcomes included into the interval. This is not possible. I mean, the frequency cannot depend on, the probability cannot depend on an arbitrary choice of the interval. It's impossible. And so this points out that I need to improve my definition. So I cannot define probability for a continuous variable in the way you see on the screen, by computing the frequency and assimilating probability to the frequency of the variable falling into an interval of arbitrary length. I cannot do that, because if I do that, as I said, the estimate of probability would be conditioned by my arbitrary decision of the length of the interval. So this means that I have to improve my definition. And what could be a way to make this kind of estimation independent of the length of the interval? Do you have any idea? A possible idea is, given that, of course, the frequency would increase for increasing length of the interval. So an idea may be, why don't we divide the frequency by the length of the interval? So if I make the interval larger, I get an increasing frequency. But if I divide it by the length of the interval, then I should obtain something that is independent of the length of the interval. However, this wouldn't be a frequency, but rather a density of frequency. Because once I divide the frequency for the length of the interval, I would end up with a density of frequency, okay? So if this frequency here is divided by 2dx, let me just show it here, okay? So if the frequency is divided by 2dx, which is the length of the interval, here, what you see here is the length of the interval, then what I obtain is a density of frequency. And by the way, keep in mind that while probability frequency is dimensionless, if I divide by the length of the interval, the estimate, the density of the frequency is no more dimensionless. It has the dimension that is determined by the unit of x, because I'm divided by x, and therefore the unit of x gives the unit of the density of the frequency. Okay, what I just defined in this way is the definition of probability density. I just defined the probability density. So the density of frequency can be assimilated to the density of probability. The definition is not complete. Now, why it's not complete? Because let me move to the website to show you the formal definition. You will see that there is an addition. So first, if we indicate the probability with the capital P symbol, we indicate the density with the lowercase p. as you see on the screen. Okay, the first equation on the top, it's lowercase p of a given value of the random variable x. It's given by the density of the frequency. Look at what is written in the ratio. Okay, I am indicating with the mouse the ratio. It's the density of frequency. Okay, which is equivalent to what I wrote in the graphical blackboard. But here there is the addition. I refer to infinitesimal value of dx, infinitesimal value, because I want to make this estimate completely independent of the length of the interval. So in order to make it completely independent, I compute the density, the probability density for a limiting value of the length of the interval. Limiting means tending to 0. Okay, good. And now let's make then this computation into R. Okay, into R. But before I make the computation, look what is written here. What I just anticipated. The probability density is expressed in units of 1 over x. Okay. Good. Now, in order to make it clear, let's do it into R. Okay. Let's split the domain of our variable that we generated into intervals, small intervals, and let's compute the density of frequency, which I assimilate to the density of probability. Before I go to the computation, do you have any question? I anticipate my plan today, and I want to make the computation for into R for a very synthetic case, like the random variable that I generated. But then I want to make another application by using real numbers and with the real meaning numbers that correspond to real world experiments. Okay, so I want to get a series of observations. I will refer to the Po River flow. The Po River is an excellent case. And then I will compute the probability density. But let me do it first for the synthetic artificial case, okay? And the instructions to be used into R to make it are written here, okay? So let me make a cut and paste. I already generated with the function runif my sample of 1 million numbers, but let's do it again, okay? By using precisely what is written here. So what I'll do is continuous cut and paste. This is not really cut, copy and paste. I'm copying from the website and I am pasting on the R console. Okay, let me clear the console here and let me paste it. Paste. Okay, for some reason I'm not getting, let's see. Okay, I made the paste with Control V, so with the keyboard, because for some reason it didn't allow me to make cut and paste with the mouse. I don't understand why, but it's not important. Look at one thing. When I generated before, I used just runif 1 million, okay? If I wanna change the range, because if I just use the function runif without any additional argument, the generation is in the range 0, 1. Let's make it in a different range. And if you want to specify the range, you have to give the range with additional arguments, as you see here, 0, 10. So now the generation is in the range 0, 10. And in fact, if I plot it, let me see, and I want to plot it only for the first fraction, PD1, let's see, 1, 100, okay, and type equal line, okay. You see on the window, on the graphic window, that I get the plot showing that the variable is indeed ranging in 0, 1, okay, perfect. Now let me go back to the web page and copy the second instruction, okay. Now you see here the probability density of the random variable falling into the interval 0, 0.1 can be computed with this instruction. Now let me copy it, okay, copy, and let me paste it here, and let's discuss it a little bit. You see here length, okay, length of the vector. What vector? PD1, but with some conditions in order to make the selection. So the first condition is PD1 greater than 0. Okay, this greater or equal than 0. This wouldn't be really necessary because we generated numbers in the interval 0, 10. So this condition, this first condition is completely, in this case, it's not needed, but for clarity, it's there. And PD1 less than 0.1 divided by 1 million, okay? So you see here the density, and actually, it's not really the density because to compute the density, I should divide this frequency divided by 0.1, which is the length of the interval. So this is the density, okay? Okay, and let me just see, okay. Now let's move forward. Okay, now with a cycle, we can compute the probability density over the full range of X and put the result in the vector PD2, okay? Before I move forward with the cut and paste, let me just make a check. Okay. Yeah, should be okay. Let me just make a check. I want to make sure that everything is fine here. Okay. So let's look at this cycle. So first of all, we need to define a vector because when we want to use a vector into R, we need to define it first. So let me define it by just saying that the vector PD2 is equal to 0. And then there is a fourth cycle here. Look at how the fourth cycle is created into R with this instruction that I highlighted. And then I'm computing for each. So basically, it's a cycle of 100 times 100 routines. In each routine, I compute the frequency, the probability density, the frequency density, probability density in a moving sub-interval. Okay, look here. The condition is expressed depending on the index I. I is varying each cycle. In the first cycle, you get, in the first routine, you get I equal 1. In the second round, you get I equal 2. In the third round, I equal 3, up to 100. And then you see that the position of the interval depends on the variable I. So each round, you get the interval moving along the range 0, 10. For instance, let's look at the last cycle where I is equal 100, okay? What is the interval? The interval starts at 0 plus I minus 1, 99, times 0.1. So the interval starts at 9.9 and the interval finishes at I 100 times 0.1, 10. So you're getting the last interval, okay? The frequency is divided by 1 million. This is perfect. And then divided by 0.1, okay? So let's copy it. 1 second, here the instruction in the fourth cycle is included between curly brackets, okay? I suggest you to always do that because the curly bracket, they identify the content of the fourth cycle, okay? The content of the cycle. Okay, let's copy, let's paste. Let me clear the console. Let me just remind you generation, and then I can make this computation. Okay, and that's it. We did it. Okay. Now, let's look at PD2, the result, PD2. Very good. Now, if you look at this result, you see that the numbers are more or less equal to 0.1. Okay, 0.1. Good. Let's plot it. Okay, plot PD2 type equal line. So look, it looks like the plot is fluctuating, but you see it is fluctuating in a very, very tiny interval. So basically the plot is constant, is more or less constant, okay? And which means that the probability density is not much varying. Look at the numbers here, not much varying in the domain of the variable. Is this reasonable? Yes, because the numbers that I generated are distributed with identical chance of occurrence in the interval 0-10. So it's identical probability because the function of R unif, look at the console, I am selecting the function, R unif is generating numbers with uniform probability over the range. So I am expecting that the probability density is constant along the range. For completeness, let me try to repeat what I did with a generation of numbers that doesn't correspond to a uniform probability. Okay, so let me clear the console and let me generate again the random numbers, 1 million, but let me generate it just without giving any additional argument, but instead of RUnif, let's use RL norm. So how are these numbers generated now? For those of you who are already familiar with statistics and probability, I generated from the log normal probability distribution. It's not uniform. It's not uniform probability. It's something different. And we will see how the probability of the log normal distribution is distributed. Let me just show you a plot, an example plot. Okay. You see that if you look at the plot, you understand that the probability is not uniform. Okay, there is something different with respect to what I generated before. So let's compute the probability density then. And then I can make control paste. Once again, I repeat the same cycle. And let's look at the vector PD2 now. Okay, I have the plot of PD2 here, plot PD2 type equal line. Magic, The probability density is not uniform. Is not more uniform. And what can you observe here? So let me just check. Waiting in the lobby. Okay. Let me just check, make some consideration on the plot that I obtained. Okay. First, remember this is a probability density, not precisely a probability, but it's clear that it gives to you an indication of the probability. So what is the most probable value? And here in this plot, you can see that the most probable value here, the plot with the value with the higher density, it's a value that is around I would say 3, probably 3, maybe. There is a function into R which allows us to compute the value with the highest probability. Let me see if I remember it. Mod PD1. Let's see. I'm not sure. Let's see. It's not. It's not mod the function. Let me just see, because mod is. Let me just check what is our project. What is the name of the function? Mod of a vector. Modes of a vector. Okay, let's see what is the instruction. Okay. It's okay. It seems like capital M. Mode with the capital M. Let me check. Mode PDI. I am expecting a mode value with maximum probability, as I said, around 3. Okay, let's see. No, it's not. Let me check. It's okay. Is what's okay. No. It's not this one which I was looking for. Let's see. Major represents the video. No, it's the video with the most density is a model. Mod X. Let me see. Is a model X. I don't understand why here it says that I couldn't find the function. Okay, let's forget about it. Okay, we will investigate it later. And anyway, the value with the highest probability should be around 3. Okay, it is this one. And then if I look at this plot, what I can see is that there is a low probability, but still possibility that I get very high values. You see, if the most probable value is 3, I still see some probability of getting a value like 100. Let's look at the max of the vector PD1. Indeed, you see that the max is 154. What does this mean? It means that even if the average of PD1 is low, it's not very large. Okay, the average is, I'm expecting something like 10. No, it's even less than that. The average is 1.65. Okay. So even if the average is low, I get a max that is very large. So this means that if this was a natural hazard, intensity of a natural hazard, I should be concerned, because it means that occasionally I can get an intensity that is very large. And these distributions, these probability distributions, density distributions, these probability density distributions that occasionally show that I may get very large values are called long-tailed long-tailed probability distribution. And why long tail? The reason is clear. If you look at this plot, you see that the probability distribution has a long right tail, right? Because the other tail, which is the left tail of the distribution, is very short. So the long-tailed distributions, which are quite common for natural hazards, are concerning. These considerations allow you to understand that probability estimation has a value in terms of technical relevance, in terms of climate change assessment. If climate change has a long-tailed distribution, I mean, it's concerning. So think of the global temperature. The global temperature increase from the pre-industrial period is 1.3 centigrade degrees, okay, which is not much. But what if somebody told you, if I look at the spatial distribution, I see that the spatial distribution of global warming, which means not the global value, it means the specific value in specific regions, the spatial distribution is long-tailed. This is concerning. It means that there might be hotspots where the temperature increased much more. And actually, this is what we are observing. Okay. So you see that in this way, we can estimate the probability density of given values. Okay. Let me go back to the website here. Here. Okay. Is the plot instruction. Now, it is also interesting to plot the cumulative probability. How can we estimate the cumulative probability? I mean, look at how the density is defined. Here, you see probability density, lowercase p, is defined by dividing frequency times, dividing the frequency by the length of the interval, okay? If I want to get the cumulative probability, which is the probability of not exceedance, what should I do then? It's clear. I mean, if I indicate the density, and let me put it in the graphical window, okay? So just 1 second. I want to copy this definition here and put it in the graphical window, okay? Good. 1 second. Okay, and then the graphical window is here. Let me copy the probability density here, edit, paste as new layer. Okay, here it is. So this is the probability density, which was computed in the interval that you see on the graphical window. How can I get the probability of not exceedance? Look at how the density is defined and try to follow me. Let's suppose that I want to compute the probability of not exceedance of 0.3, okay, like you see on the screen. Okay, try to follow me. I am writing with the mouse, so I will not be very clear. Just 1 second. I will not be very, how to say, very artistic. Okay, probability of not exceedance of 0.3. 0.3, okay, can be computed in this way by using probability density. And this is a nice feature. It's a nice, a nice way to demonstrate the usefulness of probability density. I have to compute the integral. Don't be concerned because the integral is a sum between 0 and 0.3. 0.3 of what? The integral of lowercase p x, 1 second, x in dx. Why? Because look at how lowercase px is defined. If you compute the integral, basically, forget the limit for now. Basically, you take the probability density, which is obtained by a frequency divided by the length of the interval. You multiply the probability density by the length of the interval, and then you get the frequency. And this frequency is summed up through the integral between 0 and 0.3. So I am computing the frequency of the variable to fall between 0 and 0.3, which is the probability of not exceedance. So if I compute the integral of the probability density, I get the probability of not exceedance. Let's do that into R then. And this is what is written in the web page. Look here. Here, the instruction says plot what? The cumulative sum. This function cum sum into R computes the cumulative sum of the probability density, which I computed before, times the length of the interval. Okay, and you see it's the integral over the x. Let's copy this and let's put it into R. And let me paste it here. Plot cum sum of it, and this is the cumulative probability. It's the probability of not exceedance, and you see it's varying from 0 to 1, which is perfect. So if I want to get the probability of not exceedance of 20, it's about 0.7. Which means that I have, if it was 0.7, the probability of not exceedance of 20, it means that the probability of exceedance of intensity 20 is 0.3. So you see what is, the usefulness of this approach, the clarity. The definition may be lengthy and maybe a bit cumbersome of probability density, but you see that at the end of the story, it's very clear. Do I want to get the probability of the Po River flooding Ferrara? Okay, perfect. I take the time series, the observations of the Po River flow, and then I can get the probability of not exceedance of, which is also equivalent to the probability of exceedance of the Levy level. It is very simple and very clear. I think now the best thing is to make the exercise not by referring to fictitious variable, artificial variable, but by referring precisely to the Po River. Okay, and this is relatively, it is ready. If you go in our website and you go back here and you go to the exercises, computation of the probability density function for the Po River at Ponte Lagoscuro. Ponte Lagoscuro is close to Ferrara, by the way. Okay, so we can download this. Before I move forward with the exercise, questions? Let me just look at the chat. No questions. Okay. Okay, that's fine. So let's open this exercise. And once again, if you click there, you download a zip file. Okay, let me open it. In the zip, you have a text file. And let's open the text file and show it. Just numbers. This is river flow of the Po River. I will tell you in a moment what river flow is, okay? Just numbers at Ponte Lagoscuro. And here there is a text. Let's read it, okay? Computation of the probability distribution for the Po River at Ponte Lagoscuro. At the river cross-section of the Po River at Ponte Lagoscuro, mean daily river flows were observed since January 1st, 1920, up to December 31st, 2009. Data expressed in cubic meters per second are reported in the text file Po Ponte Lagoscuro, which is the one that I just opened. Data observed on February 29th of leap years have been removed in order to make every year the same length of data. The student is kindly requested to estimate probability density distribution with R for the overall observation period, and we stop here. And then if you want to move forward, it is also required to estimate it, the probability density distribution, for two different time periods obtained by splitting the observation period in two windows of equal length. Okay. Estimate the cumulative probability distribution for the same time windows and plot the obtained distribution in graphs. Okay. I think I need to give you a short introduction to the process we are analyzing. When we talk about climate change adaptation, we need to adapt to several different risks induced by climate change. One possible risk is the risk of flooding, and this exercise refers to the risk of flooding. One other possible risk is the risk of drought, okay? And also the risk of drought can be estimated basing on river flows. Other risks are, for instance, extreme wind velocity, extreme wind storms, and then you need data of wind velocity. Other possible risks are given by hot waves, risks induced by climate change, hot waves, and then in this case, the random variable that you analyze is temperature. So the first thing, when you get a commitment, a task to be done regarding climate change adaptation, is identify the risk, okay? And as I said, flooding, drought, hot waves, etc. And then once the risk is identified, you have to identify the random variable describing the event, the risky event. So for flooding, the random variable typically is either water level, river level, also called river stage, or river flow. I will tell you in a moment how flow is defined. For extreme wind, the random variable is wind velocity. Okay. For other risks, you have to identify the random variable describing the probability of getting the extreme event impacted by climate change. Okay. So in this case, we refer to river flow. River flow can be used to describe drought risk or flood risk, typically. What is river flow? Okay. Let's see if we can obtain an easy definition in Wikipedia. Okay, let's search in Google. River flow Wikipedia. Maybe not, but let's see. River flows, no, this is a film. Stream flow, okay. Maybe this one, because river flow can be, it's a variable that may have synonyms, so can be indicated also with the term stream flow or river discharge. Let's see stream flow if we have a definition. Okay, and let's see, I don't think, let's see, sources. Yeah, it's not defined. Okay. No, it's defined here. It's not precisely the definition, but it tells how it's measured, which we can take as a definition. Stream flow is measured as an amount, volume, I would say, of water passing through a specific point over time. And typically, for rivers, the point is a river cross section. You understand, the river has a dominant direction of flowing, which is called the longitudinal direction. And then if you take the perpendicular in the horizontal plane, it's the transversal direction, which is identifying the crossing direction. So what is stream flow or river flow? It's volume of water passing, volume of water per unit time passing through a river cross section. You see that the units used in the United States are cubic feet per second, while in most other countries, cubic meters per second are used. It's volume per unit time, okay? So let me just go to the graphical window and make you a very simple sketch. Okay, and let me take a new window, a new one. Perfect. So if you look over a river, let me take a blue. Usually the river over a map are identified with blue line. This may be a river over the map, okay? And you see that there is a dominant direction of flowing. So if you go here, for instance, the dominant direction is this one, okay? And this is called the longitudinal direction. If you take the perpendicular to this, okay, you identify the transversal direction, which basically cuts the river perpendicularly to the longitudinal direction. So now, if I look at the river in this direction here, if I look at the river from downstream to upstream, and I look at it over the vertical plane, what I get is something like, let me change the color, something like this. This is the river cross section, okay? Perfect. And you can identify here the water level. Like for instance here, the water level is horizontal. So this is the river cross section, okay? River cross section. And you see that the way I identified the cross section is such that the water passes through the cross section. So what is the river flow? Perfect. The river flow is defined in this way. Okay. River flow, volume of water per unit time passing through a river cross section. Okay. In our case, the cross section, usually the cross section is identified with the name of the closest town. Okay. So in our case, the river cross section for the Po River is Ponte Lagoscuro, Po River at Ponte Lagoscuro. Ponte Lagoscuro is the last measuring station of the Po River, so it is conventionally taken as the closure section, okay? So you can measure the river flow in a cross river section, and this is what people usually do by using measurement techniques. We are not interested now in measurement techniques. What we are interested in is that at Ponte Lagoscuro we have a very long series of observed daily river flows. What does this mean, daily? Daily means that each day a measurement is taken, and the measurement is taken as the average for that day. Okay, very good. Now let's go back to our exercise then. Okay, so 1 second, the text was somewhere here, I think. Yes. So what we have to do here, it's we know how to do that. Estimation of the probability density, we just did it. So what we have to do is to upload the data, okay? Upload the data into R, and then compute the probability density with the instruction that we just used. Okay, very good. Let's do it. Before doing everything, it will take just a few minutes because you have seen it, it's very quick. Before doing anything, let me upload the data into R. And in order to upload the data are here. Okay, inside a zip file, I need to extract the data file and put it in my desktop, for instance. Okay, so I need to extract it. I right-clicked over the zip file, extract. Of course, in Windows, it's very similar, the procedure, but maybe slightly different because I am using a different operating system. Be careful of putting it over the desktop, for instance, okay? So I'm putting it in my desktop, extract. Okay, good, it was completed. And now I can go into RStudio and upload it, okay? Let me clear the console and let me define the directory session set working directory into RStudio. Click over session, click over set working directory, and choose directory. Okay, and I select my desktop here, desktop, choose. Perfect. You see here in the console, we got an instruction, set working directory desktop. You have to do the same in Windows, okay? Now we can upload the data. Let me check in the website if we have a suggested R file. Let me check it. No, we don't have a suggested R file, so we have to make it from scratch, which is, it's fine, okay? Okay, so now we have to upload the data file. So let's use the scan forever. You may source the data file from this, from the menus, but let's do it with the scan function, which is very simple, scan. Now I need to put the file name between commas, and let's see, PO. You see that with the tab, I completed the name of the file. Let me do it again. So I have to put the file name between commas, okay, and here, okay. And in order to, the file name is already in the desktop directory, and therefore I don't need to set the path. I remember that the file name was starting with PO. So I put the first two letters, and then I press the tab, and the name of the file is completed. I don't have to skip anything because it's a file with just numbers. So that's it. We can plot it just to check. When you use real data, real world data, my suggestion, the first thing that you have to do is to make a plot. So plot forever. I press the tab, okay, and here I get it. Type equal_lan. You see here the plot of the forever. Why? The first thing that you should make is a plot. This is needed because you can check if you made any mistake. By looking at the plot, you can see that apparently it is reasonable. I don't think we made any mistakes so far. Okay, but if we made some mistake in uploading, etc., you can check it with the plot. Okay, now what we have to do is first to understand the range of the variables. So let's, first of all, this is river flow, so it's varying from 0 to an upper value. Probably it doesn't reach 0. If you make the minimum of per river, if you compute the minimum is 168 cubic meters per second. Anyway, let's start from 0. It's not a big issue. And the max, important, the max, because I need to know the interval. The max is about 10,000, okay? So I have to compute my probability density between 0 and 10,000. Let's split it in, I need a 4 cycle. And the fourth cycle, I think we could use an interval of 50. So an interval of length 50 to compute the probability density. And 10,000 divided by 50 is, it means 200 intervals, which is okay. It's okay. Okay. In order to compute the density, I think the best way is to use the instructions that I used before, the fourth cycle that I used before. Okay. And let me go back with my history, and I use arrow up to go back with my history and get the fourth cycle. Here it is. Okay. I need to correct it. Let me check if I can make okay, the correction of everything. Okay, first of all, let me select another vector for the density. So like d per river is equal to 0. Now, the fourth cycle, as I said, is extended over 200 intervals. Okay. The density is called d per river. And then I should estimate the length of per river, the frequency of the vector per river. And I have to put here per river is greater than, here I have to put 50, the length of the interval. And per river is here again 50. Now I have to put 50 here, 50. And here it's not 1 million, but it's, if I well remember, is 32,850, the length of the vector per river. Okay. I think this should be fine. Maybe I made a mistake. I'm not sure. Let's see. First of all, everything went fine, so no apparent mistake. Okay. Let's plot it then. Plot d per river and type equal line. Fine. Okay, this is my density. Good. Okay, very good. And the density as a unit. So don't be concerned by the very small values of the density. As I said, the density as a unit. What is important here is the shape. It's long-tailed. The most probable value is around, I would say, 30, 40. The average, okay, there is one thing to say. The horizontal axis is not correct, because the horizontal axis, it is an index of the vector, indicating the position of each value into the vector. If I want to put, to be correct, I have to put the river flow in the horizontal axis. Okay, so let's remake the plot. D per river is the vertical axis, and here I have to put the horizontal axis. So the horizontal axis is a sequence, the vector starting from 0, reaching 10,000 with a step of 50. Look at this new function, sequence 0, 10,000 with a step of 50. Let's do one thing here. Before making the plot, let me copy this instruction so I use it later. And before making this instruction, let me just show you the sequence function. Sequence 1, 10, 1. See, 10 values, okay? And then the sequence 0, 10,000, 50. This is what you get. this sequence has a bit of a problem because it's not 10,000 long. Okay, let's see. Let's try to plot, to make the plot, okay? Okay, you see that there is an error. The coordinates, the length of the coordinates differs because the sequence it's not 10,000 long, it's 10,000 plus 1. So I think here what we should do is the sequence starting from 50. And then I should get it. And then you see the plot, okay? So let's again look at the plot. The plot has the max probability density around, I would say 1800. There is a chance not negligible of getting a value of 10,000. So the probability distribution is long-tailed. And basically, we completed the first step of our exercise, which is fine. One thing, into R, there is an easy way to do that. Plot density or either type equal line. You see, there is a function density which computes the density distribution. With respect to the previous graph, you see that it is smoothed. The previous graph, which is here, was a little bit too rough. This one is smoothed because it depends on the length of the interval. Okay, so probably the density function adopts a different length of the interval, or maybe that the density function makes a smoothing of the graph. Anyway, the estimate is okay, is similar. I may also compare them. Okay, so previous plot, new plot, lines, adds a line to the current graph. Let's put it in red, color red. Yeah, sorry. You see the comparison, they are very similar. Good. I'm not completing the exercise. I leave to you the continuation. If you are interested, you're not obliged. At the exam, I don't ask anything about exercises. My suggestion, if you want what is the purpose of continuing the exercise? To show that when you estimate the probability distribution from data, from real world data, there is some approximation. If you split the series into two chunks, you will get two different probabilities, which means that there is uncertainty in estimating the probability from data. Okay. Perfect. Now, one final thing for this lecture. Let's go back to the website. One final consideration about probability. So we don't talk about probability definition, estimation anymore. Okay. And let me just go back to our graph that we obtained. So we got these probability distributions, and look, knowing probability density is the same thing. You have seen that we can get probability by integrating probability density. So once that you know the probability density, or you know the probability distribution, and vice versa, okay, it is equivalent. Let's say that in some cases it's useful to get the probability density. In some other cases, the probability distribution, which gives to you the probability of not exceedance. Okay. The probability distributions that I got here, and you can see on the graph, they were derived by assimilating the probability to the frequency. So they were derived from the data. It may be useful that you describe these distributions with an analytical relationship, because the analytical relationships allow you to make the analytical computations, estimation of probability for a given value, estimation of cumulative probability through integration, more directly. So it is useful that you give a mathematical expression to the red line or to the black line here. And of course, the mathematical expression should be able to reproduce these lines. And these lines have a defined shape, the length of the tail, etc. So it's important that you reproduce well these behaviors. So the literature has proposed several analytical functions to approximate probability distributions. These are called precisely probability distributions. So let's go on the website. You see a probability distribution or probability function is an analytical function that assigns a probability to a considered random event or random variable. To define a probability distribution, one needs to distinguish between discrete and continuous random variables. We will focus on the continuous case. And here there are two examples. The Gaussian or normal distribution, okay, which is very useful. It is a distribution that has the shape that you can see here, the density, okay? You see that it's not particularly long-tailed and it's symmetric. The left tail is equivalent to the right tail. Here you can see different shapes for the normal distribution. And why different shapes? Because this is the analytical formulation for the density. You don't need to remember it by memory, absolutely. Just remember that the most common probability distribution or probability function is the Gaussian distribution, which is symmetric. It is bell-shaped. And this is the analytical formulation, which depends on two parameters, mi and sigma. And why two parameters? Because it allows to shape the probability distribution to the considered problem, or to fit the probability distribution to the considered problem. By changing the parameters, you can adapt, you can fit the distribution to your data. So most distributions have parameters because this allows you to adapt the probability distribution to your data. And in particular, in the normal distribution, the two parameters are the mean and the standard deviation. Please read here, everything is explained, okay? It is explained what is the standard deviation, what is the mean. And there are other distributions that can be used, the log normal distribution, for instance, the uniform distribution, which basically gives uniform probability to the whole range. And then the next time we can start by talking about the relationship between P, V, and D. Anyway, I will make a reminder at the beginning of the lecture about the Gaussian distribution. I am done for today. Do you have any questions? No questions. Okay, let me close the video recording.